Hey guys, we are going to start off with kinetics by having a little introductory discussion. And this introductory discussion is all factors that affect reaction rates. Now, first of all, let's talk about what kinetics means. When we're discussing kinetics in chemistry, it's all about how fast or how slow a reaction takes place. And that's what we're going to focus on here. How fast or slow a reaction takes place is its rate. So now let's talk about these factors and how it can affect a reaction's rate. How can it make it slow? How can it make it fast? So to help demonstrate this, I want to show you this little simulation here. Whenever we have a reaction, we have our reactants and our products. Now, in order for our reactants to convert to products, we must have both of these reactants here make a collision. Now, any collision will do. What you have to have is what we call an effective collision. So I want to look at some different things that must be taking place in order for there to be an effective collision. And if we have an effective collision, then our reactants can convert to products. So if you look over here at this little diagram, you might remember this from thermochem. We have our reactants energy here, we have our products energy here, and from our reactants to our products, that is the activation energy. Now, in order for our reactants to have a collision that is effective, meaning that it's going to break these bonds and form new bonds, we have to overcome this hill. And this is something that we talked about in thermo. So let's look and see. Watch this graph and let's pull back this knob. Let's make both of these reactants have a collision. So see where my energy bar is right now. That's the green bar on that graph. Let's pull that back and you see that these are now making a collision. The total energy that you have, however, hasn't made it to that top of the hill, which is what we call the activated complex, the transition state. Because of that, you see how we do not have sufficient energy to overcome that hill, right? So let's try this again. Let's reload this launcher and let's pull back this knob. And now let's raise that total energy bar past that activation energy point. So just right past that. Let's let it go. And looky there, we have a collision here. This is called an effective collision. What we have is our reactants make the collision and can convert to products. Now it is going back and forth, and that's okay because we have these double arrows. That means it's going back and forth at equilibrium. All right, so that is one thing that must happen in order to have an effective collision. We must have sufficient energy to overcome this activation energy here. If we don't have that, then we won't be able to have our reactants transition to our products because we haven't made it to that transition state. Now, that's one thing. Let's try something else. Let's reload this launcher and let's set angled shot. All right. So I'm going to angle this a little bit. And let's say that we do have sufficient energy. So I'm going to pull this knob back. Let's see if I can get it to work. Pull that knob back. Let's pull with enough energy to overcome the activation energy. And let's let it hit. Well, maybe it'll hit. Might need to change my angle a little bit. So let's reload that launcher again. All right, let me move my thing and enough energy and boom. So you see how, yes, we have a collision. We have our energy bar that is over the sufficient energy it has sufficient energy to overcome activation energy, but it wasn't an effective collision. The reason why is because you had an angled shot. That collision basically just glanced the other reactant. In order to have an effective collision, there's a second criteria that must be met. Not only do we have to have sufficient energy to overcome the activation energy, but we also have to have proper orientation. Now, what that proper orientation means is that you have to have a head-on shot. So a head-on shot, boom, proper orientation with sufficient energy, both of those things combined will give you an effective collision. So what I want to do is I want to pause this little simulation and I want to go back to our notes here. And on our notes, I want to add the two criteria that must be met in order to have an effective collision. So, step one, we said that you must have sufficient energy. I'm going to write in cursive because that'll help me. Sufficient energy to overcome activation energy. And remember, activation energy, I'm going to just say E sub A for activation energy. That is the amount of energy that must be overcome. It's from your reactants to your products to reach your transition state. And when you've reached that transition state, that peak, that's when your reactants can convert to products. So that's the first piece of criteria that must be met. The second piece of criteria that must be met is that you have to have, during your collision, proper orientation. So that means that those reactants have to collide at a certain point, most likely head on. If you have both of these happen, you will have an effective collision. Well, now that we know we have effective collisions and the criteria that must be met, let's look at these factors here: concentration, temperature, pressure, surface area, adding an inert gas, adding a catalyst. Let's look at these factors and see how it can correlate with these effective collisions and what that does to the rate, meaning what does that do to the speed at which the reaction takes place. So let's go back here to this fast simulation and let's reload our launcher and let's go to our rate experiments. So for the very first experiment, let's say we have multiple reactants. So we'll add, let's say, we will add 5 A's and we need some BC's. Let's add 5 BC's, all right? And let's see if we put that in there, let's see what happens to our experiment. So we have them in there. They're making collisions. Right now, we don't see any effective collisions. If they hit with the correct orientation and sufficient energy to overcome the activation energy, then we will have effective collisions. So I don't see any yet. We'll wait for just a second and see if we have any effective collisions. All right, I'm not quite seeing any. So let's just kind of end this experiment and let's try to alter something in this experiment. So instead of starting with 5 of A, let's start with maybe 20. Let's start with maybe 20 of these as well. Now our initial temperature is pretty cold, all right? Let's begin in our experiment and let's see if we have any of those collisions that are effective. So there's our experiment. I see that we are making some of my products, as there's the current amounts. We've converted to 4 of these products. So we have some sufficient or some effective collisions. Now we have 5 products. Now, what was the difference? What we did at the beginning, we had a certain concentration of those reactants here. When we did our second experiment, what we did is we increased our concentration. So what effect does that have on our rate? Well, if we increase our concentration, we increase the probability that there's effective collisions here. And if we increase that, if we increase the number of effective collisions, then we increase the rate. So the rate of the reaction happens a lot faster. So let's go back and look at concentration. So concentration, how does that affect my rate? Well, what it does is concentration increases my rate. Well, how does it do that? Well, you have a greater probability of having these two things happen. Sufficient energy to overcome activation energy. You have a greater probability of proper orientation. So due to the greater probability of these two pieces of criteria, you have a greater probability of having an effective collision. And if you have an effective collision, you have those reactants converting to products. And so that is why anytime I increase the concentration of my reactants, I increase my rate. That means the reaction will happen faster. Now let's look at temperature. So I'm going to go back to the simulation again. Let's start with maybe 10 of these guys here. So there's 10. And let's begin the experiment. Let's say that our experiment is very cold. So let's take that down. Notice what's happening to the total average energy there. This is meaning the kinetic energy of those molecules. We know that now, since we covered thermochem, that kinetic energy and temperature are directly related. So as the kinetic energy is increased, the temperature is increased as well. That means the movement, how fast or slow these molecules are moving inside here. So we have our temperature cold. We have 10 of both A and BC, our reactants. So let's begin our experiment and see what happens. You see how these guys are moving fairly slow, right? So because they're moving slow, they don't have very much energy here. They probably don't have a great probability of having an effective collisions. So now, let's say I have that same amount, but let's say I increase this experiment. We increase the temperature of that experiment. So we have 10 in there. They're moving around faster. Wow, look at that. We have lots being converted here. And the reason why they're going back and forth is just because this is an equilibrium experiment. So what does this tell us? Well, if we increase the temperature, then that also increases the rate. So I want to go back to my notes here. Increasing the concentration increased my rate. Well, increasing the temperature increases my rate as well. Now, how do we justify this on a free response? Well, we increase the temperature, which makes a greater probability of proper orientation and sufficient energy to overcome activation energy. Therefore, you have a greater probability of effective collisions, and that is what causes rate to increase. So whenever I'm discussing this stuff on free response, you have to talk about these two pieces of criteria and the fact that if the probability of those are greater, we have a greater probability of effective collisions as well. So now that we've kind of seen that we can look at these collisions, we can look at these molecules and see what's happening, let's see if we can guess what pressure will do. My little experiment doesn't work with pressure. So if I increase pressure, let's say I took that simulation and I squeezed all those together, all right? Do you think I'll have more effective collisions or I will not? Well, the answer is that I will have a greater likelihood or a greater probability of effective collisions. So if I increase pressure on a system, then I'm going to increase the rate. Now we have to be careful, all right, with this, because what are the things that can be pressurized? I can't pressurize solids, I can't pressurize liquids, but I can pressurize gases. So when we're increasing pressure and how it affects the rate, we have to be working with gases because those are the only things that can be pressurized. For my next one, surface area, I'm going to abbreviate that to SA. Let's say I increase surface area. So maybe I have some sort of solid and I crush it up, I pulverize it to where more of those particles are exposed. What do you think will happen to the rate? Well, if you've guessed right, my rate should increase. So if more of those particles are exposed, that's what you're doing when you're increasing surface area, then the rate goes up as well. The next one is adding an inert gas. So we have to talk about what an inert gas is. An inert gas is a gas that's non-reactive. It's basically just there. Okay, some examples of inert gases are like helium, neon. They're just really small gases. They're really stable, so they don't need to react or anything. Anytime you're adding an inert gas has no effect. It's there, but it's not reacting. It's not really getting in the way. So inert gases have no effect on the rate of a reaction. The last thing is adding a catalyst. So what does a catalyst do? Well, if you remember from our thermochem unit, what a catalyst does is lower the activation energy. So I want to just refer to this FES simulation here. So a catalyst lowers this activation energy here. So instead of my activation energy having to go all the way up that hill, maybe my activation energy just goes here, and then I can convert to my products. Okay, so this would be my pathway now. Now, the reason why a catalyst lowers activation energy is because it creates an alternate pathway for the reaction to take place. So I'm going to kind of just sketch out one of these graphs again and just show you kind of what I mean here. So let's say we have an exothermic reaction, and so our activation energy right now is from here to here. So it's from a reactants to the products. That is our activation energy. Now, we have a catalyst coming along. What a catalyst is going to do is not change anything but my activation energy. It's going to lower the activation energy. So now I just have to go this way. And it does that by creating an alternate pathway for the reaction to take place. It's basically like a shortcut. So let's say that we were trying to drive to the stadium from the high school parking lot. Now, so here's our stadium, here's our school, right? Now, we have this nice little nifty bridge that we could go across, but let's say we didn't have that bridge there. How would we have to travel to get to the stadium? Well, we'd either have to go down Deerfoot Parkway, Happy Hollow Road, Trustful Clay Road, back to the stadium, or we'd have to go Deerfoot Parkway, turn on Trustful Clay Road at that red light to get to the stadium there. You see how we have to take a long journey to get there, right? Long journey. Now, this is if we did not have that bridge. But if we do have that bridge there, let's say our bridge is the catalyst. You see how it's providing a shortcut. It's providing an alternate pathway. All we have to do is boom, boom, go out the parking lot, go over the bridge, and we're at the stadium. We have a shortcut, a shorter pathway for us to take place. And because of that, we have lowered our activation energy. So a catalyst increases the rate. And how does it do that? It increases the rate because it lowers your activation energy by providing, that word says providing, an alternate pathway. So when we explain catalysts on exams, we want to say all of this. What a catalyst does, it increases our rate. How does it do that? It lowers the activation energy by providing an alternate pathway. And so that is why when we add catalysts to things, it makes reactions happen faster. So I hope this was a little bit helpful for the factors and how it affects the reaction rates. I know in the notes I have something about a bleach demo. We're actually going to do a lab later on when we're working with kinetics and bleach, and so you guys will actually see that demo by doing it yourselves. I hope this was helpful, and I hope to see you in class soon.